Okay, up until now, we've been talking about primarily galvanic/voltaic cells where there's spontaneous reactions. We're going to talk a little bit about electrolytic cells, which are non-spontaneous. So an electrolytic cell is a non-spontaneous redox reaction, meaning that we need to put power in. To drive the reaction. And this is not just you have to put a little bit of energy to get over an activation energy curve or hump. This is you have to put in energy constantly the entire time to get it to move. It should be a little bit more like pushing a big stone up a hill or pushing a couch across a carpet. It's not going to push itself. It's not going to keep going once you start pushing it. So you have to keep putting energy in the entire time. An example of electrolysis is the electrolysis of water. So assuming that you've got the right mixture of water, you can run electrical current. So here we've got a battery. That's our external source of power. We've got a positive, we've got a negative, and at our anode and cathode, we've got oxygen bubbles and hydrogen bubbles being produced to make oxygen gas and hydrogen gas. So we're breaking the H2O up. That's this one here. H2 and O2 combined together spontaneously. We can go the opposite direction by putting in electrical current. This is something that you could, in theory, do at home, but I recommend not trying at home, probably because bad things can happen when you combine electricity and water. There's probably a way to do it safely at home, though. But the products also explode, anyway. Other things that you can do with electrolysis, other than breaking up water, is you can use it for electroplating. So, for example, the reduction of naturally occurring metal oxides can be used to produce pure metal. You can do this with sodium metal by doing the electrolysis of molten sodium chloride. We'll look at some molten salts later. You can also plate metals onto other metals. So you may have encountered or seen or heard of like jewelry or things that are, it's maybe, I don't know what the core would be actually, but it's some cheaper metal on the inside, and then they just put gold or they put silver on the outside, and then it looks like silver or gold, but it's much cheaper because it's not all the way through. And so this is much less expensive. There's also applications where you might want a thin layer of silver or gold or some other metal on a cheaper metal because you just need that surface contact. And you can do this with an electrolytic cell. So again, we've got a voltage source, we've got a silver electrode that's going to be putting silver ions into solution, and then we've got the object that we want to be plated that's going to be picking up the silver ions in solution. We don't have a salt bridge here because we are actually trying to move our silver from this electrode to the other electrode. So we want our ions to be flowing around in solution instead of having them completely separated. A voltaic cell, the spontaneous reaction for a zinc and copper voltaic cell proceeds spontaneously. We've got 1.10 volts, and this is the typical electrochemical cell that we're used to seeing. So we've got our anode, oxidation occurs at the anode. Oxidation is losing electrons, it's pushing electrons through the wire. Cathode is where reduction occurs. Reduction is gaining electrons, and so we're adding copper to this copper electrode, copper from solution. So we've got our oxidation, we've got our reduction, and that's for the voltaic cell. The electrolytic cell is the opposite in many ways. It's not in all ways. It's opposite in terms of direction and labels. So we are adding in a voltage source. We're not measuring a voltage source out. We're not harnessing a voltage source that's coming out. Instead of our electrons flowing left to right, we've got them flowing right to left. And our names have switched. So our cathode is now on the left, our anode is now on the right. It's the same metals setup. The electrodes are the same. The salt bridge is the same. All that's changed is the direction that the electrons are flowing, and the cathode and the anode have switched labels. But at the cathode, we still have reduction occurring. So the zinc ions in solution are picking up electrons coming through the wire to form zinc metal. And then our anode is still where oxidation is occurring, and so our copper is going into solution as copper 2+. So we've switched to the directions that things are flowing, but the electrodes are still in the same spots. A brief summary of electrochemical cell types. In all of our electrochemical cells, oxidation occurs at the anode, and oxidation is losing electrons. So that's where the electrons are going to flow from, the source of the electrodes, or the source of the electrons. And reduction occurs at the cathode. So we've got our red cat mnemonic that the book recommends, and oxidation and anode both start with vowels, so those go together. Reduction is gaining electrons, so that's going to be the side where the electrons are flowing to in terms of our wire. In our voltaic cell, the anode is the source of electrons. That's where the oxidation is occurring, and the cathode's drawing the electrons. In our electrolytic cells, electrons are drawn away from the anode. In our diagram, it still looks like it's the source of the electrons. Right, they're flowing away from the anode. So the idea is the same. And that's connected to the positive terminal of the power source. So we've got our positive lead here drawing electrons. Pulls electrons from our anode, where oxidation occurs. And the electrodes are forced into the cathode that's connected to the negative terminal. So we're supplying a lot of negative energy, negative charge, that pushes electrons into our cathode so that reduction can occur. Which of these statements is true for both electrolytic and voltaic cells? Is it that the cell spontaneously produces a positive voltage? Is it that electrons flow from the anode to the cathode? Is it that oxidation occurs at the cathode? What do we think? B. Why is it B? Or maybe a better question, why isn't it A? Or why isn't it C?
Because there's a possibility that cells could be non-spontaneous?
Yeah, so for A, the cell spontaneously produces a positive voltage is only true for voltaic cells. Our electrolytic cells, by definition, need energy put into them. They're non-spontaneous reactions. So that's only true for voltaic cells. And for C, oxidation does not occur at the cathode. Where does it occur?
The anode?
Yeah, it occurs at the anode. So C is just always wrong. If we're doing electrolysis, adding current, adding voltage into a system to drive a non-spontaneous reaction, we can predict the electrolysis products, and it's going to get a little bit hairy. This was not my favorite part of this chapter. So one possibility is that we've got pure molten salts. So presumably this is going to occur at really high temperature. in my mind, it's got to occur at really high temperature because we're melting salts, and salts have really strong intermolecular forces. So in pure molten salts, the anion is oxidized, convenient. The cation is reduced, convenient. Those fit with our definitions of anode and cathode as well. Remember that the anion is negatively charged. It's just a negatively charged ion. And cation is positively charged. There's other ways to figure this out other than memorizing those definitions. So let's look, for example, at sodium chloride. If we have sodium chloride, this is going to exist as Na plus and Cl minus if we separate it out into the ions. So we're going to have Cl minus, we're going to have sodium plus. Cl minus already has all of the electrons that it's going to want. It would be very difficult to add another electron to Cl minus. So it can't be further reduced. It can't gain another electron. And so it has to be oxidized. We can take an electron away from it. And the way that we would do that in our electrolysis cell, or electrolytic cell, is we'd have chloride in the molten salt, sort of in a solution, not really a solution, but we'd have chloride. It would react at the surface of the anode to give up an electron, and in the process it would form chlorine gas. So that's where the electrons are going. They're going into the anode, and then it forms chlorine gas, which is stable. So that's why it's perfectly content to lose electrons, or content enough that we can drive that reaction. And then on the other hand, we've got sodium, Na plus, can't be further oxidized, right? Can't lose more electrons because it's already gotten down to its noble gas configuration, but we could give it another electron. So it can gain an electron to form sodium metal. And so we'll end up plating sodium onto our inert electrode as the sodium that's in solution picks up an electron and reverts back to its metal form. Or you can just memorize the anion's oxidized and the cation's reduced. However, we also can have situations where our molten salt contains more than one cation and possibly even more than one anion. We'll look at that soon. And so we have to consider which of the cations is more easily reduced. Which one more easily gains an electron or electrons. And so we can refer to our standard reduction potentials. And our less negative / more positive, however you want to think of it, the one that's higher up on the list, electrode potential, is easier to drive. Or complete, however you want to think of it. It more easily accepts an electron. So just picking two from our book, if we've got sodium chloride and potassium chloride in solution, we've got two cations. Cations are going to be reduced, red cat. Cations are going to gain electrons, and so we're looking for the one that's easier to drive in the forward direction. And the ordering is going to be the same as in our, forgot to silence my phone. The ordering is going to be the same as in the standard electron potential, standard reduction potential table. So sodium having a less negative value is easier to drive in this direction. It's not going to be spontaneous, but at negative 2.71 volts, it will drive a little bit easier. It will be a little bit easier to run in the forward direction than potassium. So we're choosing the less negative one. So we would expect sodium to be reduced at the cathode and come out as sodium metal. Do we have questions so far? If we finish this lecture and you're confused, it might be helpful to go back and read through it another time or two. It took me a few tries when I was reviewing it to get my brain to understand it a little bit more. If we have more than one anion, or negatively charged ions, we can determine which one is more easily oxidized. And oxidation is losing electrons, oil rig. Oxidation is losing electrons, or losing electrons, oxidation, Leo goes grr. So for example, if you've got sodium bromide and sodium chloride, bromine and chlorine, we've flipped these. From how we would see them in our standard reduction potential table. So we've got these already flipped in the oxidation direction. Oxidation's losing electrons, so the electrons are on the right side. We would have pulled these out of our reduction potential table, flipped them, and changed the sign for our E with the 0. And we're going to choose the more positive one. So in this case, this is going to be bromide. Bromide has the less negative value. And so it is going to require less voltage, less power, basically, to drive, to get it to work in this direction. It doesn't want to work in this direction. That's why it's an electrolytic cell. But it will if we put in enough energy. We have to put in a little bit less energy to get bromide to lose an electron versus chloride to lose an electron. So if you're given the reduction potential, you're going to need to flip it to the oxidation and then choose the less negative one. Or you can just choose the less positive one on the reduction potential table, and that would also work. So less negative oxidation potential if you're flipping the reduction potential equation reaction. Or the less positive reduction potential. Either way works. The book will give you the reduction potential even if it's showing oxidation, or if you know that it's the one that's going to be oxidized. So you will have to do a little bit of critical thinking to figure out what you need to do. We don't just have molten salts. Molten salts are a little bit easier because it's just the salts. We also have aqueous solutions. I think we're more likely to encounter aqueous solutions. And electrolysis in aqueous solutions is a little bit complicated because, as we saw previously in this lecture, water can also be split with electrolysis. And because of that, we also have to consider the possibility of water undergoing electrolysis. And we've got two equations that correspond to the electrolysis of water. So it can undergo oxidation to lose electrons, and it can also gain electrons by going through reduction, and these have different E0 values. So these are the standard reduction potentials or the standard oxidation potential, I think, for this top one. If we're in pure water at room temperature, our concentrations of H plus and hydroxide are not standard, so our actual E cell or electrode potential is going to be something more like negative 1.23 volts. However, pure water, which neither you nor I have ever encountered, although I've come close, pure water doesn't conduct electricity very well. It's got like mega ohms of resistance, which is really high. But if you add an electrolyte salt, charged ions, something that can conduct electricity, then electrolysis can occur for the water.
What is pure water?
Pure water is just H2O. All the water that you've ever drank in your life has electrolytes in it, partly because your body needs electrolytes. If you drink pure water, like, it'll leach some electrolytes out of your body, or I think it can. So it's generally advised to not drink like distilled water because that's relatively low concentrations of ions, but there's probably still a little bit in there. All right, so an example, if we've got a sodium iodide solution, this is an aqueous solution, we have to consider a couple of things. So we've got our possibility for water to undergo oxidation and to undergo reduction. We also have our salt. So we've got our sodium iodide, we've got both of our ions. Those can also undergo oxidation or reduction. So this is why it's a little bit more tricky than molten salts. We have to consider which is going to undergo oxidation or reduction. Is it going to be our water, or is it going to be our cation or anion? So the half reaction that occurs the easiest is the one that will occur. So for our oxidation, we've got these listed out in the oxidation direction. So H2O giving up electrons, iodide giving up electrons, iodide's an anion, anions undergo oxidation. And we've flipped the values from the book. So the less negative of these is going to occur. So we expect that our iodide is going to form iodine gas. And for the reduction side, we've got sodium versus H2O. H2O's got a much less negative electrode potential. So we would expect that we will get some reduction of water. So if we have what the slide here is calling active metals, cations of active metals, sodium would be an active metal, they can't be reduced from an aqueous solution because the water is going to be reduced first at a much lower voltage. Here's what that might look like in an aqueous salt solution. So we've got this line in the middle just separating our sides. That wouldn't actually be there in the solution. It's just one solid solution or one continuous solution. We've got our voltage source. We've got the negative side supplying electrons. We've got the positive side seducing electrons from our other electrode. Our anode is the one that's doing the oxidation. It's giving up electrons, it's driving electrons, losing electrons, and our cathode is the one that's receiving the electrons. In this case, we've got inert electrodes, probably platinum or some other metal like that. Our anions are being oxidized on our anode, and water is being reduced at the cathode, because water is going to be reduced preferentially to sodium metal. So if we tried to do this to get sodium metal to plate onto our cathode, it wouldn't work. We would just end up generating H2 gas and hydroxide. We'd end up with a basic solution. Questions? Another complication that you can run into if you're trying to do electrolysis is overvoltage. So for reasons beyond the scope of the class, some non-spontaneous reactions need extra voltage to occur. So our example here, H2O getting oxidized to form H plus and O2. We would expect its value, its electrode potential, to be about negative 0.82. The actual voltage for the oxidation of water is about 1.4 volts. So rather than having to put in 0.82 volts, we would need quite a bit more than that at 1.4 volts. Other things that we can do with electrolysis, if we have a setup where we know that we can plate something out, we can reduce a metal out of solution to put it onto another object. We can set up an electrolytic cell to do that. And electrons are going to act as a reactant, and they're going to also have a stoichiometric relationship. I often just call this a ratio, balance equation ratio, with the other reactants and products. So we know we can calculate how many electrons we would need, or how much amperage, how much current we would need to get a certain number of moles or grams of our metal out of solution. So in an electrolytic cell for copper plating, the half reaction is that Cu2 plus, copper 2 ion reacts with 2 electrons to form copper. So we need 2 moles of electrons for every 1 mole of copper that we would want to get out of solution. And if we were doing this in an electrolytic cell, we would suspend our whatever we want to be coated. It would have to be metal. On one side, we would put that on the reduction side, the cathode side, the negative voltage. And we would have our copper, whatever we want to plate on it, in solution so that it can get reduced onto our object here. And hopefully it does that evenly. But the takeaway, right, we've got a ratio between our electrons and the thing that we are trying to plate. The thing we're trying to pull out of solution and put onto our cheaper metal to make it look cool or whatever. Since they are electrons and they're charged, we're going to measure their quantity, the number, with charge instead of mass. And we've got a couple of things that are going to be helpful. We're going to do one example for this. So we've got a couple of helpful tools. We've got our Faraday's constant. This relates the amount of coulombs, a unit of charge, with the moles of electrons. So this is sort of like Avogadro's number. It functions similarly. But it's for electrons instead of for atoms or moles. It's relating charge and moles of electrons. And then we also have that 1 amp is a coulomb per second. Also useful information. And we can figure out a total amount of charge using a relationship with our moles of electrons to charge with Faraday's constant. Figure out our total charge, and then figure out either the time or the current being amps that we need to make whatever we want happen. We'll do an example. All right, we want to do some silver plating, let's say. Silver plating uses the reaction of the silver ion plus an electron going to silver metal. How many moles of electrons do we need to run through an electrolytic cell for silver plating in order to plate 3 moles of silver? So we're trying to get 3 moles of silver out. How many electrons, how many moles of electrons do we need to drive that? We're trying to get 3 moles silver, and we want to know how many moles of electrons. What's our relationship between silver metal and electrons? What's the ratio? 1 to 1. We've got no coefficients in front of our silver or our electron, so it's a 1 to 1 ratio. So we would have to put 1 electron in to get 1 silver out. So it would be 3 moles of electrons. What if we were trying to plate 1.5 moles of copper, knowing that copper 2 plus 2 electrons goes to copper solid? How many moles of electrons would we need to do that? We've got to guess for 3. So we're going to be starting with our 1.5 moles copper. And we need our relationship between copper and electrons, the thing that we're trying to change to. Our ratio is 2 to 1, 2 electrons for every 1 copper. So we would need to put in 2 electrons to get out 1 copper. So it should be 3 moles of electrons. So it's a process that we've done before. Hopefully we're experts at it. It's just a new context. All right, let's add a couple more steps. Silver can be plated out of a solution containing silver ions according to this half reaction. How much time in minutes would it take to plate 12 grams of silver using a current of 3.0 amps? A couple of things that you'll need for this that you would have on your information sheet. Faraday's constant, 96485. Is it 58? It is 85. coulombs per mole of electron. 1 amp is 1 coulomb per second. I think you'll also have. I'll give you some time to give this a try. All right, so where to begin? Any ideas? Yeah, we can turn our grams into moles. We've basically got 3 pieces of information we've been given. We've got our reduction half reaction. We've got 12 grams of silver. We've also got 3 amps. Great place to start is converting 12 grams of silver into moles of silver. So we're going to divide by 107.868 grams per mole. This will give us the number of moles of silver. So we've got 0.111 dot 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 moles of silver. We just learned that we can relate, we can convert with stoichiometry between silver and electrons, and that's our next step. Our ratio from our balanced equation is 1 to 1, very convenient, nothing to put into our calculator. So we need 1 electron put in for every 1 silver that we take out of solution. So 0.111 dot 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 moles of electrons. The other piece of information that we have, or another piece of information that we have, is that we've got 3 amps. And it might be helpful, I think it's helpful, to switch this to be 3.0 coulombs per second. That will be important in a little bit. But currently we've got moles of electrons, 3 amps, switching it to coulombs per second doesn't really help us out because we don't have moles of electrons in here. What does have moles of electrons in it though is our Faraday's constant. It's got moles of electrons down here on the bottom. If we multiply the moles of electrons that we have by Faraday's constant, that will give us an amount of charge in coulombs. So we're going to multiply by the Faraday's constant. (96485). Get a large number. 10,733 and some change coulombs. And this is where the coulombs per second version of amps comes in handy. Coulombs per second has seconds in it. Seconds is a unit of time, of course. So we can convert from coulombs to seconds using this 3.0 amps. And the way that we would do that, since seconds is on the bottom in amps, we need to divide by amps to get the seconds to flip to the top. So 3 coulombs on the bottom, 3 coulombs every 1 second, dividing by 3 amps, and they'll still give us a number of seconds. I'm just going to go ahead and round it a little early. So about 3,577 or 78 seconds. We wanted time in minutes, 60 seconds per 1 minute. This would be about 59.6 minutes. So it would take about an hour at 3 amps, which is deadly, Took about an hour to plate out 12 grams of silver. Questions about parts of that? It's mostly just look at the units and figure out how you can cancel out the units that you have to get the units you want. All right, almost there. Another relevant process when talking about electrochemistry and redox reactions is corrosion. Corrosion is the undesirable oxidation of metals exposed to oxidizing agents of any kind in the environment. Rust is an example of corrosion. Rusting, rather. So oxygen, as it turns out, is easily reduced and can cause the oxidation of other substances, especially metals, metals that just get left out in the environment will oftentimes oxidize. We've got two reduction reactions, one with water, one with acid, H+. And we can see that the one with acid has a much higher standard electrode potential, so 1.23 volts instead of 0.4 volts. So that's going to reduce more easily. It's going to oxidize metals more easily, more spontaneously than if we just have water. Despite their ability to be easily oxidized in the presence of oxygen, acid, and water, metals are great for building things. One of the ways to keep them from oxidizing is just keep them dry. That's not always an option, though. Many metals are going to form oxides that coat the surface of the metal, basically acting like what we might do for paint. And that actually protects the metal from further oxidation. So if you make the layer of metal thick enough and take into account that it's going to oxidize on the surface, it's not necessarily a problem. And that can prevent further corrosion. For example, aluminum forms an aluminum oxide coating. It's highly inert. It's also structurally solid, and acts as a protective coating. Another famous example of coating the surface of the metal is the Statue of Liberty. The Statue of Liberty is made of copper. It was initially that copper brown color, and then because of all the seawater and other things, has turned to the iconic green that it is now. However, this is not always the case. Oxides of iron, aka rust, tend to flake away from the underlying metal. So instead of forming a protective coating, the surface kind of starts to peel away, and it works its way into the metal further until it's no longer structurally stable or solid. This is why Cybertrucks that aren't painted are a bad idea, I think. Also why cars are always painted. If you've ever seen a car that's not painted and it's got rust spots on it, those are just going to continue to get worse and work their way through the body of the car until you don't have the surface of the car anymore. Or for things like this sheet metal on the outside of this dilapidated, presumably abandoned building. I don't really want to talk about this slide. Corrosion's not that interesting to me. Sorry if it is interesting to you. But you can read about this if you want. Moisture does need to be present for rusting to occur. That's iron corrosion. Water is a reactant in one of the reactions, and charge also needs to be able to flow freely. Charge cannot just flow freely through the air. We need things to be able to move around. If you add more electrolytes, that's going to promote rusting. because charge flows easier. And so cars are more likely to rust quickly in places where the roads are salted, so in New England, the Northeast, or in coastal areas where there's seawater mist present because there's salt water just all over the place. So like around here, you don't have to go and get like the undercarriage of your car sprayed down. In New England, Massachusetts areas, right? They've got places where you can go and get the underside of your car washed to help prevent rusting of parts of your car that would not normally be exposed to water. The presence of acid is also going to promote rusting. Lower pH enhances the cathodic reaction, and that's this, what we were looking at here on this first corrosion slide. We've got a much higher electrode potential if we've got acid present. So that's going to much more easily, much more quickly, much more spontaneously cause the oxidation of metals. So things like acid rain would be bad for that. There are some ways to prevent the corrosion of iron, and this is a major industry. So one way is just don't let it get wet, or don't let it get wet for very long. So like if you have a cast iron pan, it's got iron in it. You don't want it to be wet for long periods of time unless it's got a good coating on there. Even so, you still don't want it to be wet for a super long time because it is going to be more prone to rusting. Another thing you can do is coat it with a substance like paint, or in the case of cooking, with oil to protect the cast iron pan. Just anything that will keep water out. You can also use a sacrificial electrode. This is a metal that oxidizes more easily than iron. I don't know whose video it is, but there is a video about the use of sacrificial electrodes in like dams in the Netherlands, maybe. But basically there's like these huge underwater walls that they've got that have iron on them. And to keep them from rusting and from degrading and falling apart, they basically just screw on big electrodes that are going to rust preferentially to iron, and they just swap those out every now and then. And it's a lot cheaper because they're able to use cheap building materials. Iron's very cheap, it's all over the place. And by using sacrificial electrodes, they're protecting that iron from corroding. So I think that's cool. Another thing that you can do is you can coat the iron with a metal that oxidizes more easily, like a layer of zinc. And zinc is good because the zinc oxide acts as a protective coating. So where the nails or whatever other material you might have used would normally flake away because it's rust, the zinc oxide, just because of the way that it is, will form a protective coating. And then you just have zinc oxide basically as a, not really a paint layer, but a protective layer on your metal. This is a question that we can answer if we had a standard reduction potential table. Which of these does not act as a sacrificial electrode for iron? Our options are copper, magnesium, zinc, manganese. This is probably more easily answered if you've got standard reduction potential table, but we can maybe make a guess. Got a guess for copper. Which one do we know it's not? Zinc, right? We saw that on the previous slide. It's definitely not zinc. I would guess that it's magnesium because it's an alkaline earth metal. I don't know if that's the answer because I forgot to look it up, but that would be my guess. You can check the conceptual connections section in your book. It's at the end of the chapter. There's all the answers to the conceptual connections in your book. Any questions before we wrap up electrochemistry? Okay.